Okay, we just spent some time dealing with equation solving, mainly with rational functions in this particular section, but we've also spent quite a bit of time solving polynomial equations as well in this chapter. Ultimately, if we want to solve a polynomial inequality like we did for our opener today, it's essentially going to be the same type of methods that we're going to use for equation solving. So ultimately, the first thing we want to check out here is that just to make sure we know what a polynomial inequality is. If we have some polynomial that's greater than or equal to or less than or equal to 0, okay, then to solve that, okay, we want to just find the values of x that make the polynomial positive. Okay, if it was less than 0, we want to find the values that'll make it negative. So like I showed in the opener today, when we look at this graph, okay, the bigger picture on this is that when we have this curve greater than or equal to 0, all we want to do is find the places like this area and this area over here where this is greater than 0, in other words, when it's above the x-axis. Okay, if we were to just do this same problem over again and had it to be a less than 0, then we would have wanted this part and this part, okay, the parts that are below the x-axis. Okay, so bigger picture-wise, that's all we're looking for is when is this polynomial above the x-axis or when is it below the x-axis. And if we can find the zeros, okay, the zeros are where it changes, okay, from one to another. Okay, so let's take a look at an example here. They give us f of x to be x plus 3 times x minus 4 squared, which is a cubic function, as we know. If we were to expand that, they already gave it to us in factored form, so that was nice of them because that makes the zeros easy to find. And ultimately, we're going to determine the real number values of x that cause f of x to be 0, positive, and negative. Okay. Now, the first part of this, part A, would be the zeros, of course. And we have plenty of experience with that at this point. We know that the zeros here are going to be negative 3 and 4. 4, of course, would have multiplicity 2. True? Okay. And remember what we talked about on the graph, if we have something that's multiplicity 2, okay, when we graph this thing, we should expect that this hits the x-axis and turns back around. Okay. Anytime we have multiplicity 2, which we'll see when we do our analysis in a minute. Okay. And then to answer the other questions for when is this positive and when is it negative, okay, and this also can be used to solve the problem we did in the opener, which we'll revisit in a minute. Okay. Okay. We can essentially make a number line with the zeros on it. Okay. So I'm going to make a number line with my zeros on there. Okay. I'm going to put f of x on the right here because this is what I'm testing. This is going to be kind of a test, if you will. Okay. And we call these, I call them, the zeros here, I call them split points. Okay. So our split points are going to be our zeros. So however many zeros we have, we're going to put those on the number line. Those are going to be our split points. And then what we're going to be after here is, okay, what is going on in between the split points. Okay, and there's only 3 different areas in this particular case that we have to worry about. We need to worry about what's going on before we get to negative 3. We got to worry about what's going on between 3 and 4, negative 3 and 4 that is, and then also between 4 and infinity. Okay, so what we're going to do is we're going to pick a test point, okay, that's somewhere in this group right here. So something that's less than negative 3. So you can pick really whatever you want. Okay, let's pick negative 4 because that's less than negative 3. If I were to plug a negative 4 in there, and remember, I don't need to come up with a value here. All I need to know is it positive or negative? Is it above the x-axis or is it below the x-axis? So if I put a negative 4 in here, I'm going to get a negative answer here. Negative 4 plus 3, that's negative 1. And if I put a negative 4 in here, I'm going to get a negative, but it's going to get squared, which would make it positive. So it would be a negative times a positive, which would make it a negative. Okay? So it would be a negative in that group. If I were to pick something between 3 and 4, and what number is between 3 and 4, that would be nice to put in here. Could put 2. What would be even better than 2 or 1? How about 0? 0 would be the easiest one to plug in, probably. So if I put a 0 in there, that's going to be positive. Okay, this is going to be squared, so it's still positive. So positive times positive gives me positive. And then if I put something bigger than 4 in there, like say 5, I'm going to have positive here, which is going to give me also what? Positive. Now, you'll notice that we do have that behavior that I mentioned here where at 4, it's positive on the left side, but it's also positive on the right, because what did we say, since this is multiplicity 2, okay, it's going to hit the x-axis and go back up. Okay. And the other thing we should know about this, since it's cubic, Okay, with cubic functions, all cubic functions with a positive leading coefficient have to have end behavior like that. Okay, have to be going down as we go left and up as we go right. So does that make sense in this picture, that left of -3 that we're negative, going down, and right of 4 we're going up? That matches up with what we know about cubic functions too, doesn't it? Okay. So ultimately what we've done here then is the analysis that we've done, okay, has allowed us to essentially solve, okay, 4 different inequalities here. So let's look at the 4 that I mean. Okay, if we were to have been asked that we want to go, when is this, let's say, greater than 0? Okay. When is that greater than 0? Without looking at the graph, okay, the answer is right here in front of us. Okay. If it's greater than 0, it's going to be any of these areas where the signs are what? Positive. So my answer to this would be -3 to 4. Okay. And from 4 to infinity. Now you'll notice I didn't include -3 or 4 because we need what? We need greater than. We don't want the zeros to be part of that because the zeros equal 0. They're not greater than 0. Okay. How would that change then if I had x plus 3 times x minus 4 squared if I wanted greater than or equal to 0? Well, I know for sure that -3 would be part of it. Okay. And then the other part of it is, do I need to have 2 different answers for this part? If I'm going to include 4, okay, couldn't I just say from -3 to infinity? Okay, that would include that 4 that's in there, wouldn't it? Okay. So in this case, I wouldn't need to separate those two. I could just say from -3 to infinity, it's greater than or equal to 0. Because what's going on at 4? It's equal to 0, isn't it? Okay. Similarly, if I had been given the inequality, when is that less than 0? Again, our number line tells us the answer. When it's less than 0, it's going to be whenever we have a negative sign. So it would be less than 0 on -infinity to 3. Okay. And then if I change that to or equal to 0, what would be the only thing different? What would be going on at -3? It would be included, so we'd have to have a bracket, wouldn't we? Okay. All right. Questions so far? Okay. So again, can this be done with any polynomial? Yes. Okay. The only problem that we have, though, is that this is going to rely on the fact that we can actually find what? Zeros. Okay. If we can't find zeros, then we're not going to be able to make this number line, are we? Okay. So in the case that we had earlier, okay, it turned out that this one does have some nice ones. We'll do this one algebraically next, but ultimately, if this didn't have nice zeros, if you will, we'd have no choice but to get the decimals for the zeros and approximate what those intervals would be. Okay. All right. So let's take a look at that original problem that we started with today, which was x cubed minus x squared minus 2x, and we wanted greater than or equal to 0, I believe it was, right? Okay. All right. So if we were to do this algebraically, okay, we would recognize that it has an x that we could factor out, which would leave us with x squared minus x minus 2, and that we could also factor this into x and x minus 2 and plus 1. Okay. So if we were to do this algebraically, that's how we would start. We would write the factorization if we could factor it. Hopefully we can. Okay. And if that's the case, then we got 0, 2, and -1 would be our zeros. And when we make our number line this time, we would put all 3 zeros on there. Those would be our split points this time. And then our test points, we could pick something to the left of -1, like -2, for instance. So plugging in, and I usually put them in the factored form. It's a lot easier to decide whether they're positive or negative if you put it in the factored form. So -2 in here would give me a negative, negative, negative. So negative, negative, negative would mean negative. Between -1 and 0, like -1/2, that would give me negative, negative, -1/2 in here would be positive. So it would be a negative times a negative times a positive, which would be positive. 1 would give me positive, negative, positive, which would be negative. And then anything bigger than 2 would be positive, 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 which would give me positive. So just like we did from the graph that we showed a few minutes ago, okay, we are going to be greater than or equal to 0 on -1 to infinity, or not to infinity, but to 0. and then also from 2 to infinity. Remember, it was an or equal to, so we do include the zeros. And that's exactly what we see here. Negative 1 to 0, we're above the x-axis, and then from 2 to infinity, we're above the x-axis. Okay, so same answer. Okay, 1 with an algebra approach. Okay, and we started today with a graphical approach. Okay, but again, if you have a graphing calculator and you have to do it algebraically, is there any reason why you shouldn't check it with the graph also and make sure that what you say is the truth is really the truth? All right. Okay. Let's take a look at I want to look at in your book. It's on page 258. Right towards the bottom, they give us a function that's in the blue box. That's 2 times x minus 2 cubed times x plus 3 squared. And what we're going to do with this polynomial, it asks us to use knowledge of n behavior and multiplicity of real zeros to create a sign chart and sketch the graph of the function. And it says check your sign chart using the factor method of example 1, which is what we just did. Okay? And then we're going to sketch it with a calculator and see how we did. So first of all, I'm going to make a list of my zeros. Okay? We know that we have 2 and negative 3. It's already in factored form for us. Okay, so since we have 2, it's multiplicity 3. And negative 3 would be multiplicity 2. Okay. And let's go ahead and make our chart and see what we got going on here for f of x. We have negative 3, we have 2, and again, whatever they are, make sure they're in order from left to right when you draw this number line. Okay. So let's see what we get when we put something in here that's less than negative 3, like negative 4 for instance. We would get a negative cubed, which is a negative. And we would get something squared, doesn't matter what it is, it's going to be positive. So we'd have a negative times a positive, which would be negative. And between these two, we could put in 0. 0 would give me negative 2 cubed, which is negative. Okay. And then this would be also positive. Okay. And then anything bigger than 2 is going to be positive, positive. So we'd have positive here. Okay. All right. So that said, if we were to try to develop a graph here, we know that we have something. We have a 0 at negative 3. We have a 0 at 2. Okay. We also know that this function is going to be what degree? If we have 3 here and 2 here, if we were to multiply those together, we would have, if I multiply x to the 3rd times x to the 2, that makes x to the 5th. Okay, so this should be a 5th degree function. Okay. All right. And ultimately, I know that n behavior-wise, it does have a positive leading coefficient, right? So if it's 5th degree, it should be going down on the left, up on the right. Okay. All right. We also know that at negative 2, okay, we have a multiplicity of 2, and negative 3 we have, or excuse me, I said that backwards. Negative 3 we have multiplicity 2. At 2 we have multiplicity 3. Okay. So knowing that, we know for sure that it's going to look something like that. Okay. Question is, what's going to be going on near the origin? Okay, based on what we know about the multiplicity. So let's review by graphing that. So we have 2 times x minus 2 cubed, and I'm going to put that all in parentheses just to be safe. And then times x plus 3 squared. Okay. All right, so when we graph that, I'm going to change my window a little bit here. I'm going to go negative 5 to 5, so we can see a little bit closer what's happening there. At negative 3, it hit the x-axis and went back down, which is not surprising because it has multiplicity 2. Okay. When it has an odd multiplicity, remember, it goes through the x-axis. Okay. Although it has a kind of a special situation going on here, it looks like it's kind of flat in there for a little bit. Okay. It changes it a little bit in there. Okay. So ultimately, kind of, if you were to draw it, it kind of look like that. Okay. And again, from here, we know it goes up and then back down. Okay. And again, I drew it a little off here, but ultimately we'd have something like that going on here. We'd have this going on here, and then somewhere down here it would have to turn around, of course, to get back up to that part, right? Okay. If we were to graph this, could we find that point where it goes and turns around? Sure, we have a minimum command with the calculator. We could find it, of course. Okay. And so, again, somewhere down here it's going to also have a y-intercept in there somewhere too, right? Okay. All right, so with the information about zeros and with our sign chart, okay, without having to actually plot points, we could get a pretty reasonable picture of what this looks like, couldn't we? Okay. All right. Now, again, one of the things in prep for calculus is that, you know, when you see something like this is something that you just need to be able to do. Okay, you need to be able to know where the zeros are. Okay, you need to be able to know without too much time and too much effort into it. Okay, what is this function going to look like? Because if we're going to analyze this function, if you already know what it looks like based on the information that you have, it's going to make it a whole lot easier to analyze, isn't it? Okay.